class, Mr. Mohiuddin here with a video regarding position, velocity, and acceleration to help prepare for the assessments. So you're given a problem here very similar to one of those on your assessments. You're given a position function in kilometers as a function of time in hours, and it's a trigonometric function, so it's going to vary back and forth. Our question is to find the initial velocity and the initial acceleration and to include units. So one of the giveaways is this word here, initial, and that's telling us that we're interested in when time t is equal to 0. So the initial velocity, what's being asked for is what is velocity equal to 0? Oh, sorry, what is velocity of 0? And finally, when is acceleration at 0? So what is the velocity at 0 and what is the acceleration at 0? So to do that, we need to find the velocity and acceleration functions respectively. So we're given position as this thing right here, 2 sine 3t minus 4 cosine 2t. The hierarchy goes position, velocity, acceleration, right? Distance, distance per time, distance per time per time. So the derivative here, s prime of t would be, let's see, negative 2. Sine's derivative is going to be cosines, and then the chain rule would mean times 3. So minus 4 cosine's derivative is negative sine, chain rule times 2. Let's clean this up a bit. So these would combine to give me negative 6 cosine 3t, negative 4, negative, and the 2 would give me positive 8 sine of 2t. So that's going to be called either, I'm going to mix up notations here, ds dt, which is the same as velocity as a function of time. So one reason I like this notation here is it tells you the unit. S represents distance and t represents time. There's a fraction bar in between. So we know that it's going to be something per something, some distance per time, which in this case we have specific units for. So the question was initial velocity. So what is the velocity at time t equals 0? Well, that would be negative cosine 3 times 0 plus 8 sine 2 times 0. Well, sine really is sine of 0, and sine of 0 furthermore is 0, so this whole thing is 0, which is very convenient. Similarly, 3 times 0 gives us 0. Cosine of 0, if you think about your cosine wave, remember a sine wave looks like this, and a cosine wave looks like that. Or you could think of your unit circle and 0 degrees being, or 0 radians being the point 1 comma 0, either way. In any case, cosine of 0 is 1, and negative 6 times 1 is negative 6. So there's our initial velocity, and the unit here is going to be, let's see, rate of change, velocity, slope, ds dt. Well, the top here is in kilometers in this case, and t is in time. If you go back to the problem, you'll see that time is measured in hours. So there's the first part of our answer. The second question was, what is the acceleration? The initial acceleration. So we need to find the acceleration function. So we have velocity here. Let me give it a different color. Velocity is from the previous step right here. We have negative 6 cosine 3t plus 8 sine 2t. So dv dt, one could say, or v prime, or acceleration as a function of time is the second derivative, right? So this would be s double prime of t. All of this crap represents the exact same idea. How fast is the velocity changing? So velocity is already changed, so 2 levels of change there. So the negative 6 is going to stay here. Let's see, we have cosine's derivative is negative sine. 3t is going to stay still until I do the chain rule, so times 3. Plus 8 is going to stay there. Sine's derivative is cosine. 2t stays put. Party on the inside means we multiply by 2. That's the chain rule right here and right there. Simplifying, we have negative 3, and 6 and 3 will give us 18 sine of 3t. 8 and 2 gives us plus 16 cosine of 2t. And that's our acceleration function. So plugging in 0 in here, fairly bloodless. The initial acceleration is 18 sine of 30 plus plus 16 cosine 2, 0. As we just saw, sine at 0 is 0, so this entire term evaporates. Cosine of 0 similarly is 1, so we get 16. The unit here is a little curious. So remember, this is the rate of change of velocity, the derivative of velocity, or the second derivative of position. So there's a couple of ways to think about this. One thing I'll just encourage you to remember is that the second derivative is going to have a double unit of time. So kilometers is our distance per hour squared. So there's our two answers, 16 kilometers per hour squared, and up top, -6 kilometers per hour. On the site, in the next window here, I have actually the graph to show you visually how this looks. So this is a model of position. You see the function given. Here you see the velocity, or the first derivative at 0 is -6. The second derivative at 0 is 16, graphically, and here analytically. What this means in part is at 0 you have, let's see where it's 0 here. At 0 is over here. You have a negative slope, -6. And we haven't yet talked about this, but notice that this function at 0 is concave up. And the fact that the second derivative is positive, or 16, is an indication of that. So a lot to take in there. Next problem here. Position this time is given by a cubic function where f is in feet and x is in seconds. Find the velocity of the object when the acceleration is 0. Include units in your answer. So here we're told to find velocities, or our ultimate answer needs to be velocity at some value, but we don't know what that value is. So what is that value? That's going to be the solution to the acceleration equaling 0. So in order to find this, we need to know what the solution to that is. In order to do any of that, we need the derivative. So the position function is f of x, and that's 3x cubed minus 4x squared plus 2x minus 3. The rate of change of position is the velocity function. So just taking the derivative here, that would be 9x squared using the power rule minus 8x plus 2. We're going to come back to this because we don't yet know what to plug in here. The second derivative is the acceleration function. Oops, let me see all my variables. It should be x is equal to, let's see, 18x minus 8, and 2's derivative is 0. So this says when the acceleration is equal to 0, so set it equal to 0, and simple linear equation here, 18x minus equals 8 rather, so x is equal to 8 over 18, which simplifies to, let's see, 4/9. So that is when the acceleration is 0. So we now know what to plug in here. So the velocity at 4/9 is going to be kind of a beast to evaluate, but so I won't do it by hand, but here's what it would be. 9 4/9 squared minus 8 times 4/9 plus 2. It shouldn't be too bad. Let's see, that'd be 16 over 36 times 9 minus, let's see, that'd be 32 over 9 plus 18 over 9. This is really 9 times, this is really 9 times 4, so the 9's cancel, giving us 16 over 4 furthermore, which is 4. 4, of course, is 36/9. You can fast forward to this part. Just enjoying myself here. 36 take away 32 is 4/9 plus 18/9 is, okay, I'm already bored of this problem. What you get when you plug in 4/9 is this, 2/9. So I forgot to simplify it here, but you get the 0.2 repeating, which is 2/9, which would be your final answer. So this part actually, I know it got a little carried away there. You can just plug in the calculator, frankly. I'm perfectly fine with that. The velocity at the time when acceleration is equal to 0, plug it in, you get 2/9. Well, velocity is measured in distance per time. Our distance here is feet. Our time here is in seconds. And there you go. Hope this helps.